Honestly, it's the hallway track. Like, the spaces where I've learned the most at CppCon have been in the evenings, hanging out with people over a drink or at dinner and just chatting.
Right. Hi, everyone. Thanks for attending this session. My name is Dian-Lun Lin. I'm a fourth-year PhD student at the University of Wisconsin-Madison. So here in today's talk, I'm going to talk about our recent research project, Taro. It is a test graph-based programming system using C++ Coroutine. Taro allows you to enable multitasking within a test graph. Here's what I'm going to present today. I'll start off the motivation behind Taro. Then I'll present Taro's C++ programming model and dive into the Taro's coroutine-aware scheduling algorithm. I'll then present the experimental results of Taro on both micro benchmarks and the real-world application. And finally, I'll give the conclusion. All right? Taro is a test graph-based programming system. So what is test graph-based programming system, TGCS? Well, TGCS encapsulate function codes and their dependencies in a top-down test graph. Say you have a bunch of code, and in your code, you probably have some functions, tasks. For example, you have test A, B, C, and D. What TGCS does is to help you define a test graph. For example, test B and C can be executed in parallel. You can use TGCS to define the test graph. And after you define a test graph, you execute the test graph. And the scheduler in TGCS will schedule the test graph for you. If you have more than one CPU thread, test B and C can be executed in parallel. But why TGCS? What's the benefit of using TGCS? First, it is easy to write and express a test graph. So here is one example of programming a test graph using TGCS. Here I can declare a scheduler, and then say I use impress to insert this code block A. To create test B, I use impress again, and then insert the code block B, and so on and so forth. To define the dependencies, what we can do is to define a dependency between two tasks. So here, test A dot precede test B, meaning that we execute test A, and we need to finish test A before the scheduler execute test B. And finally, we schedule the task and wait until all the tasks is finished. The second benefit of TGCS is that it allows to implement irregular parallel decomposition strategies. Unlike loop-based model, for example, OpenP, that execute tasks across independent iterations. And what TGCS does is to allow you to define a test graph rather than just, say, parallelizing for loop iterations. To further improve performance, most scientific applications start to incorporate a heterogeneous set of operations, CPU, GPU, custom accelerators operations. And that's what we call heterogeneous test graph. So in this test graph, we have test B. Inside this test B, we have BC, CPU operation, and we have BG, it's a GPU operation. So inside the test B, we'll have some CPU code. We'll also have some GPU code. When the CPU thread executes this test B, we'll execute CPU code and then offload GPU code to GPU. The problem is, the challenge is, this CPU thread needs to be blocked until GPU operations finished. That is, most existing TGBS all assume a timing execution per task. The CPU thread needs to wait until this GPU code inside the task is finished. And that's really bad because, as shown here, this is a runtime example. Assume that we have one CPU and we have one GPU. So first, we are going to execute test A, and then we execute, say, BC. And we start to offload BG, and what most existing TGPS do is to, after executing BG, we then execute test C and then D. So you can see there's an idle time between BC and C, which is totally unnecessary. What we want is executing test A, BC, and then BG. When we offload GPU operations, we want to sort of multitask to test C and then D, so we can have an overlap between test C and BG, so we can reduce the runtime to achieve the best result. So how can we solve this challenge? Well, turns out C++ coroutine is the solution. Let me briefly talk about what is coroutine. A coroutine is a function that can suspend itself and resume by the caller. A typical function we all know is actually a subset of coroutine. So if we have a function, what we do is to call a function, and then we execute this function, and at the end, we return back to the caller. On the other hand, if we have a coroutine, what we do is to call a coroutine, and coroutine execute, and then suspend the coroutine, suspend itself, and then go back to the caller. And then after a while, caller resume it again, and so on and so forth. So a coroutine is a function that can suspend itself and resume by the caller. But why coroutine is the solution? Well, imagine you want to do two things when you go home. You want to boil the water to get some hot drink. You also want to take a shower. Suppose each thing is a function. Suppose you are single. What you're going to do is to either boil the water first and then take a shower, or you take a shower first and boil the water. But no matter what you are doing, when you are heating the water, you need to stay in the kitchen and wait until the water is boiling, because it is a function. However, if we are using coroutine, what you can do is to go to the kitchen and turn on the stove, and go back, multitask to take a shower. And after taking the shower, I can then check whether the water is boiling. If that is the case, I turn on the stove, and then finally enjoy my hot water. You can see there's an overlap between boiling the water and taking the shower. So conclusion, coroutine is very useful if you have a stove. Not really. Coroutine is very useful if you have other computing resource, like GPU, TPU, or you want to do async I/O. So without multitasking, in TGBS, you incur this idle time, which is totally unnecessary. However, if you are able to use C++ coroutine to enable multitasking within a task, within a task graph, you are able to overlap, you are able to reduce the runtime. And that's the powerfulness of C++ coroutine. But why not coroutine? If C++ coroutine is so powerful, why only a few people is using it? While coroutine concept is simple, C++ coroutine is not easy. There are lots of customization points, And it's just not that straightforward. So for example, if I want to implement a C++ function, I only need to define function itself. However, if I want to define a C++ coroutine, you need to define coroutine, promise, available, and you also need to use coroutine handle to manage all these coroutines. To implement a C++ coroutine, you need to define coroutine function, you need to define a coroutine class, and inside this coroutine class, you need to define a promise type to control the behavior of the coroutine. You also need to define available. You need to understand what is void await suspend and bool await suspend. You need to understand the difference between available and promise. You need to know the compiler's view, what is symmetric coroutine transfer. Of course, you need to implement a scheduler to schedule all these coroutines. And let's just too complicated. So can we have a new heterogeneous TGPS using C++ coroutine? And this TGPS should allow users to enable multitasking with a task, while abstracting away all the C++ coroutine details. And that's where Taro comes into play. Right? Before I dive into programming model, is there any questions so far? Yeah.
Is there data dependency between tasks also? Like, is that allowed?
So data is managed by users.
Like task B taking as input what task A has output.
So if task A is dependent on task B, you need to finish task A before you execute in task B. So you can also say there's a data dependency. Okay? Sure.
As in how are, I guess, coroutines communicating?
How are you mean the coroutine? How are coroutine
Let's
is?
say two coroutines have like no dependency between them or task dependency between them, except they need to communicate in some fashion.
Not sure what I'm understand your question. So, it's like, so the data is all handled by users in my case.
Okay.
Yeah. Yeah, sure.
Like the concept of symmetric versus asymmetric coroutines, right? You could pull or push data between different coroutines.
Mm-hmm.
Do you support anything like this with your schedule?
Yeah, actually, that's really interesting. So there's a computation pattern called pipeline. And it turns out you can use symmetric coroutine transfer to implement this kind of computation pattern, which is really interesting. Yeah.
Why coroutines? Why you can achieve the same multitasking with regular threads? You have scheduler, you can schedule the CC before B finishes. Like no reason for that. Like your graph, like there is like a CPU is just single line, while actually it's like a multi-threaded line. So we can actually run multiple threads simultaneously. Why?
Okay. So TGPS need to have scalability. And that is a TGPS needs to support a very large test graph. And when this very large test graph becomes heterogeneous, as a scheduler, it becomes very hard to check all these tests, whether this test is finished. So if you have coroutine, you can easily express all these things. Does that make sense? Okay. So that's why existing TGPS all assume a dominant execution, because that's the easiest way. All right? Programming model. Before we dive into a programming model, we need to understand synchronous and asynchronous mechanisms. It's like when you are heating the water, how do you know whether the water is boiling? There are two mechanisms. The first one is synchronous, which is just wait, just stay in the kitchen and wait until the water is boiling. Another is asynchronous. So for example, polling method is like you go to the kitchen and check whether the water is boiling. If not, you go back to do your own things. And after a while, you go to the kitchen again and check the status of the water. So it's like you are polling the state of the task. Another is called callback. It's like you pay extra money to buy a water kettle, and when the water is boiling, it'll notify you. So this asynchronous mechanism is where we can enable multitasking to reduce the runtime. All right, so I'm gonna define this test graph using our programming model. So here we have Y node, it is a callback task, and we have two wait node, it is using synchronous mechanism, which is simply means atomic execution. I also have polling task. And these two tasks is where we want to use CppCon to enable multitasking, to enable overlap between tasks. All right, so first, what you're gonna do is to include two files, Taro.hpp and CUDA.hpp. Here we use CUDA.gpu as an example. So first thing to do is to declare Taro, specify how many CPU threads you want to use. And you need to specify, you need to declare CUDA, specify how many CUDA stream you want to use. CUDA stream is like a task queue in GPU. So when you call a kernel, you need to specify which stream you want to enqueue. So here, I'm gonna create the very first task. So here, task A, you call in place. And inside this lambda, you call CUDA.wait. So task A is a wait task. And the wait function here takes a lambda as an argument. Inside lambda, you can offload whatever GPU kernels you want. So here, the lambda offers a string for you to offload GPU kernels. So when you insert this kernel, you will need to specify this stream, meaning that this kernel is enqueuing this stream. So our CUDA scheduler will handle all these streams for you. So here, this wait is non-multitasking. It is using synchronous mechanism, meaning that CPU thread need to wait until offloaded GPU kernels finish. All right, task B. So task B is a callback task. Here I want to use CppCon. So you need to specify, okay, this is a coroutine. Here I have some CPU work, and after CPU work, I have suspend callback. So all you need to do is to replace wait method with this suspend callback. And inside this lambda, you can offload whatever GPU kernels you want. Okay, so when the CPU thread offload all these GPU kernels, it'll suspend this coroutine and try to multitask to other tasks. So here's the runtime example. Again, BG is like kernel B1 and B2. After offloading BG, we can suspend the B and then multitask to, say, task C, so you can have overlap. Right. Here, task C is a polling task. So here I specify this is a coroutine. And then I offload GPU kernels using suspend polling. You just change the name from suspend callback to suspend polling. Okay, so after CPU offload GPU kernels, it can multitask to another task, if there's any. Here I have CPU work C1. When the CPU thread offload the GPU kernels and then suspend, you'll resume this CPU work C1 after kernel C1 finish. So to be clear, the result is is exactly the same as here. We offload kernel C1 here, and then we do synchronize. So what it means is like you need to wait until this kernel finished. And after that, you call CPU work C1. Taro guarantees you have the exact same result as shown here. But you don't need to synchronize. There's no need of synchronization. You don't have this synchronize function here, because Taro will try to multitask to another task. Okay. Test D, it is a wait task. So again, call wait function, and inside this wait function, I offload the GPU kernels. And you need to wait until this offloaded GPU kernel finished. Finally, I define the dependencies and schedule it and wait until all the tasks is finished. Let me give you another example. So here, this is a new task graph. Again, include two files, declare Taro, specify how many CPU threads you want to use. Declare CUDA, specify how many CUDA strings you want to use. And here you define test A. Test A is a callback task, so specify this is a coroutine. Execute CPU work, and then you call suspend callback. Inside the suspend callback, you offload whatever GPU kernels you want. And after the CPU thread offload these GPU kernels, it will suspend this coroutine and try to multitask. If there is no other task available, the CPU thread then goes to sleep to save power. Test B, again, this is a callback task. Specify this is a coroutine, and then offload the GPU kernels using suspend callback. And this CPU work B1 is guaranteed to be executed after kernels in test B finished. So you'll have exactly the same result as shown here. Taro guarantee you have the same result, but there's no need of synchronization. Okay. Test C, it is a wait task. So execute CPU work C1 and offload your kernels, synchronize. Test D, it is a polling task. So you just change the name from suspend callback to suspend polling. And finally, define the dependencies and execute, schedule it, and then wait until all the tasks in the task finished. So that's the Taro's programming model. Another thing I want to stress is its extendability. So here, CUDA is responsible for managing GPU streams, GPU operations, and multitasking, non-multitasking methods. Here we decouple Taro and CUDA scheduler into separate components. And this decision ensures the system's scalability and extendability. And it makes it easier to extend to support other computer architectures in the future. So, for example, in the future, I can support custom scheduler, custom accelerator by writing a custom.hpp. So here I can just change the name from CUDA to custom, and you can do exactly the same thing, just change the name. So if you implement a callback mechanism, you can use suspend callback, and inside this lambda, you can offload whatever custom accelerators operations you want. Maybe in the future, I can do hybrid. I'm not sure if there's a compiler can do this, but if I also want to do use the GPU, I can declare a CUDA scheduler, and here I can offload GPU kernels in test B. And after that, I can still define a dependency between test A and test B. And that's one of our goals. So we have three goals. The first one is simplicity. We want to let users we write the code as simple as possible. You don't need to handle promise, available. They are known to be difficult to program. All you need to do is to use the keyword cowait and suspend callback, suspend polling. Second is that efficiency. We have a built-in coroutine-aware scheduling algorithm to support our programming model, which I'll talk about later. And the third one, like I said, Taro is easy to extend to support other computer architectures. Right? Before I dive into algorithm, so is any question? Yeah.
The way this works, you're offloading to a GPU. Could that just as well be a second core of a CPU?
Second core?
Instead of a GPU, could it be another CPU, a different core, a different processor?
You mean different GPUs or
CPU?
different CPUs? You mean when you offload and when you resume, can this be resumed by another CPU thread?
Right, I don't quite understand the kernel D1. What's special about a GPU? Could it just as well be another CPU core?
Another CPU core, so when you offload the GPU kernels, you just offload the GPU kernels to the stream, and that CPU thread can work on another functions. I'm not actually understand your question.
Okay, carry on, maybe it'll become clear.
Okay, we can discuss this later. Okay. Sure.
I was wondering if you wanted to use more than one CPU core, could you have more than one of those schedulers running in different threads?
So here, when you declare like Taro, you can.
Have several threads. Each one has its own Taro scheduler. Would that work? Or?
Let me think about it.
If you had a multi-core machine, you just want to make use of more than one core for the
I get you.
You know what I mean?
Yeah. I haven't tested yet, but it should work.
Okay.
Yeah. Yeah, sure.
Does Taro currently support OpenCL, or is it just CUDA?
No, just CUDA. Yeah, Taro is just about to start. Yeah.
So I guess you'll probably get into this, but I imagine the schedule you use is a thread pool. I think that's kind of what the questions over there are getting at, is making sure that the cores on the machine stay busy. Or do you use a thread pool?
Yeah.
Yeah.
The scheduler has a thread pool.
Of course.
Okay.
Can we add our own schedulers? Like if there's a CUDA scheduler, can we add like some other scheduler that uses OpenCL or?
Yeah, so that's why I decouple Taro and CUDA. So later in the future, maybe I want to support OpenCL. We can just write another custom like OpenCL.hpp and support it.
For your hybrid tasks that do CPU and GPU, would it be simpler to have two tasks, one specific GPU and one specific GPU?
Yeah, but when you execute this GPU task, you still need to synchronize. You need to know whether this task is finished before you move on.
Yeah, sure, but I mean, from the point of view of the graph, instead of having one task that does two things, should we have two tasks?
You can still use two tasks. So I guess your question is like, can I split CPU work and the suspend callback to two tasks? Yeah, you can do this. You just need to add more dependency between these two tasks because you need to execute CPU work A1 first and then offload the GPU kernels.
Okay, and there is no downside in doing that. It's just simpler from a design point of view to group everything into a single task.
You mean which one is better?
It won't introduce some bottleneck or some blocking point into the graph?
You mean like if I create two tasks, is there any overhead? The overhead is very small because creating a task is very lightweight.
task within a task.
Schedule what?
A new task within a task.
New task within a task. Coroutine, no. Coroutine, no.
You don't support dynamic tasks.
Yeah. Right now, it's not.
You allow support for custom executors?
Sorry, what?
Custom executors?
Uh-huh.
Do you have support for that?
I would say I'm working on it. Actually, I'm working on async I/O because I think async I/O is more important. So, like I said, Taro is just about to start. So, if you are interested in this project, please get involved. It is open source.
Follow-up question. I'm used to TPP flow graph. What are you adding to this that's not in the other?
So, TPP graph is another TGCS, right?
But like, my question is, it's awesome that like all of the stuff that you've shown kind of can be done in that at the moment.
Oh, I get. So you are saying whether I can embed C++ coroutine in existing TGCS. Is that your question?
Not exactly.
Uh-huh.
I guess I was more asking of like what the MO of this is. Like what special thing are you trying to solve with Taro that doesn't exist in TPP flow graph right now?
So Taro can multitask within a task graph. Can TPP support C++ coroutine?
Not C++, I mean, maybe not, but it inherently supports work stealing from threads, right?
Yeah, work stealing. Work stealing is totally different from the concept of multitasking, right? Because, so I just want to mention the built-in scheduling algorithm is also work stealing. But what I want to say is this. The most important thing is that Taro helps you to multitask. So you can overlap. But if you use oneTBB, which I suppose it doesn't support coroutine, and you cannot do this. You just need to assume atomic execution. So you need to wait until BG finish so you can execute test C. Mm-hmm. Right. So I'm gonna move on to dive into a Taro coroutine aware scheduling algorithm. So here, I'm gonna schedule this test graph. This is example 2, like I mentioned before. These 14 lines of code and this test graph. Here, each task has some CPU operations and some GPU operations. So I'm gonna schedule this test graph. Right, so here I assume we have 2 CPU workers and we have 1 GPU stream. In Taro, each worker has a high priority queue, HPQ, which stores suspended task. Each worker also has a low priority queue, LPQ, which stores new tasks. During scheduling, each worker executes tasks from its high priority queue to low priority queue, ensure that a suspended task is prioritized over a new task. This is because we want the suspended task to be resumed as soon as possible by the same worker. Otherwise, if another worker steals that suspended task, it will induce some overhead, cache misses, CPU migration overhead. So our scheduler will be aware of that and try to avoid this happen. All right, so first step, I include task A into worker 1's low priority queue because it is a new task. And worker 1 executes task A, offload GPU kernels in task A, and then it suspends task A. And it goes to sleep because there is no other available task to work. So it goes to sleep to save some power. Next step, here after GPU kernels in test A finished, cooldown runtime will invoke the callback because this is a callback task. And this callback task will insert task A back to worker 1's high priority queue because it is a suspended task. And finally, it will notify worker 1. We do not insert task A to worker 2, otherwise it will induce overhead. Okay. So here, after executing task A, we insert task B, C, and D back to worker 1's low priority queue because they are now available and they are new. Okay, so in this step, worker 1 steals task D from worker 1's low priority queue, that is task D. So we have work stealing algorithm, and in our work stealing algorithm, a worker will try to steal a task 1 from another worker's low priority queue. Low priority queue stores new tasks that is not executed before. So stealing a task from low priority queue does not incur overhead like cache misses or context switches. If the suspended task is stolen and executed by a different worker, it will induce overhead because the task was executed by, say, worker 1 before. You need to sort of migrate the information from worker 1 to worker 2. So we try to avoid that. All right, next step. Here, worker 1 starts to execute task B, and then it overloads GPU kernels in task B, suspend task B, and then it can multitask to task C. For here, worker 2 execute task D, offload GPU kernels in task D, suspend task D, and it will create a query task to poll task D's status. So this query task is a very lightweight. All it does is to poll a task status. If task D is not finished, worker 2 will go to see if there is any other available tasks. And after a while, worker 2 will execute this query task again and then poll the status of task D. The next step, worker 1 execute task C, offload GPU kernels in task C, and it is blocked by wait method because task C is a wait task. At the same time, GPU kernels in task B is finished. We invoke, cooldown runtime will invoke the callback, insert task B back to worker 1's high priority queue. Finally, notify worker 1. However, worker 1 cannot resume task B because it is blocked by task C. Task C is like atomic execution, just like a function. For the worker 2, it polls the status of task D by executing query D. And it finds out that task D is finished, so it pushes task D back to its high priority queue. And then finally, you will resume the task D. The next step, worker 1 still cannot resume task B because it is still blocked by task C. And here, worker 2 decides to steal task B from worker 1's high priority queue because task C may need very long time to finish. Worker 2 decides to steal task B and resume the task. And finally, finish the remaining task. So this is a scheduling example for this task graph. I know our coroutine aware work stealing scheduling algorithm is efficient, yet a little bit complicated. But you don't need to worry about it. You write code, Taro will handle others for you. All you need to do is to write these 14 lines of code to express this task graph. What's more is that Taro utilized lots of efficient CppCon synchronization primitives. For example, existing TGPS use lots of condition variables. Taro scheduler is based on CppCon atomic notify. And that really further speed out the scheduling performance. So here, this is a table provided by modern CppCon by Rainer Green. So he compares the performance between condition variable and atomics. By using atomics, we can achieve 1.6 times speed up compared to condition variables. All right. Finally, I'm gonna evaluate Taro on both manycore matrix parks and the real-world application. So here's how I perform. I have 8 CPU threads, each of 3.2 gigahertz. I also have one NVIDIA 3080 Ti GPU. For baselines, in the micro benchmarks, we have Taskflow, which is a state-of-the-art test graph-based programming system. Taskflow does not support Coroutine, so to demonstrate the efficiency, we implement Taskflow Coro, which utilizes executor async. It is actually a standard async. So when a suspend coroutine is ready, we create an async task on the fly to schedule it. So you can imagine there is an overhead, dynamic overhead. Boost Fiber is a CppCon library that implements lightweight threads, also known as fibers. Boost Fiber does not have native support for test graph like Taskflow or Taro. So here we wrap Boost Fibers within our test graph to create or manage the test graphs. Here, second benchmark we use is a large-scale circuit simulation workload. We compare Taro with a circuit simulator arterial flow. Okay, so for the micro benchmarks, we consider 6 commonly used test graph patterns to measure the performance. So for example, we have linear chain test graph defines a sequence of sequentially dependent tasks. Embarrassing parallelism test graph defines only independent tasks. We have divide and conquer, which means a complete binary tree. So in each task, we have first data-driven task. So here, this is a pseudocode. The task will be repeated, that is, suspend and resumed for 300 iterations. This iterative computation pattern is very common in iterative algorithms, data processing pipelines, and simulations. All right, so here's the result. The figure on the right compares runtime growth over increasing test graph size among Taskflow, Coro, Fiber, and Taro on data-driven task. The x-axis here shows graph size, and the y-axis shows runtime. The green line is Taro. Taro performs better than other schedulers in almost all scenarios, and you can see the gap continues to grow. So here, one interesting observation I want to discuss is linear chain. So in linear chain, Taskflow can have the best performance because it is linear chain. There's no benefit of using multitasking. Taro achieved very similar performance as Taskflow because our coroutine-aware scheduling algorithm prioritizes resuming the task on the same thread. So we can avoid lots of context switches, lots of CPU migration overhead. However, if you look at Fiber and Taskflow Coro, it suffers from significant context switches because they don't have such an algorithm, scheduling algorithm to avoid these frequent CPU migrations. Another task we use is called fixed runtime task. So here we assume each task is a fixed runtime task. So this is pseudocode. We busy loop CPU functions for a fixed runtime, and then we busy loop GPU kernels for fixed GPU time. Here we want to mimic the workload that GPU involves massive computations compared to CPU. So G time will be larger than C time. Here the figure compares runtime on fixed runtime task. Still, Taro have the best performance. And here, the interesting observation is that we can see both Boost Fiber and Taro achieve very similar performance across all the task graphs. And we think that is because both methods use multitasking. And in the fixed runtime task, we don't have the iterative pattern. That will result in many context switches. In that case, the effect of our coroutine-aware scheduling algorithm is not that pronounced. All right, second benchmark, the final benchmark. Here, this is a real-world application. So this figure shows the test graph of the circuit simulation workload. In each task, so this is a task, we have 4 dependent operations. We have 2 CPU operations. We have 2 GPU operations. And in this test graph, it consists of multiple parallel lines. The test graph size depends on circuit and input sizes. Okay, so here I show the achieved speedup by Taro over RTL at different test graph sizes on 2 circuits. The x-axis is test graph size, and the y-axis is a speedup. So you can see when the graph size is small, like this, RTL is faster due to limited parallelism available, because there's almost no chance to multitask. However, as we increase the test graph size, where parallelism becomes more abundant, Taro starts to outperform RTL because Taro now is able to have more chance to multitask. The final result I want to show is memory usage. So here, this is memory usage at each second for RTL and Taro. The x-axis is the time, and the y-axis is the memory. The green line is Taro. You can see Taro requires a bit more memory usage because CppCoroutine requires extra memory to store the state of each coroutine. But you can see we don't have significant difference here. And actually that highlights our scheduler can manage this kind of memory overhead induced by coroutines. All right, so that's the final result. Here, this is a conclusion. We have presented motivation behind Taro. We also present Taro C++ programming model, and then present a coroutine-aware scheduling algorithm. And we compare Taro with different TGPS, measure the performance. And the future work here is document, and then extend. So here, of course, I want to support different accelerators. And one interesting thing is that Taro is not just heterogeneous computing, not just CPU and GPU computing. There are lots of interesting things you can do in CppCoroutine. For example, like I mentioned, you can use the property of CppCoroutine, like CppCoroutine's resume and suspend, and use that to describe different computation patterns. So for example, like I said, this pipeline computation pattern, actually, we can try to use symmetric coroutine transfer to describe this kind of test graph, which is very interesting. And currently, I'm working on async IO. So Taro is just about to start, If you are interested in this project, please get involved. And that's all I have today. Thank you again for attending this session. Any questions? Sure.
So it seems like you're trying to do two things in one task, like CPU work and GPU work, but there is no particular reason to do that. Like you can always separate it into CPU and GPU part. Like if you do that, then basically your solution is really similar to threading building blocks by Intel. Like everything you have here, you can do it there. And how your solution compares to TBB? Did you try to at least benchmark against the TBB?
I haven't. I should try. But like I said, TBB does not support coroutine, right? So TBB does not support multitasking. So, and what question is, what the biggest challenge is that task is assumed atomic execution. So when you have GPU operation in this task, when the CPU thread executes this task, there's no way for this CPU thread to jump out to this task and go to other task.
Yeah, but why is the reason to do this in one task? Like,
So you separate, okay? Let's say you separate. Okay, so you separate. So this is pure GPU task. You still have a CPU thread execute, right? You still get stuck. You don't have chance to jump out. This CPU thread have no chance to jump out.
no, like the small CPU
Mm-hmm.
task will be finished, and like it will mark as finished, and that's like it's ready to do some GPU work. Like that GPU work will be like offloaded to GPU, like as a separate task, and then like CPU can do this with the C task.
Okay, so let's say you have some GPU tasks. How do you know this GPU task is finished? You need to track, right?
Yeah.
And there's some overhead.
TBB, like it has all the structures to ensure all of that.
So there are lots of GPU tasks. Say we have a very large task graph, and there are some GPU operations in some tasks. How do you check as a scheduler? How do you check whether the task is finished, the GPU task is finished?
As far as I know, it treats basically like a GPU task as another task.
So you need to check, right? You need to keep tracking all these GPU tasks can finish. So you can, say, I know this GPU thread is finished. This GPU task is finished. I can go to another task.
Yeah, but and
There's overhead.
TBB has this scheduler, and it manages all of that.
Yeah, so there's overhead, right? You need to keep track all of the things by using.
To understand how it compares, like how is it different from TBB? Like if TBB does exactly the same, if you separate this like CPU and GPU into separate tasks.
Okay, so you mean the difference? Like I say, it's multitasking and non-multitasking.
It's also multitasking. It was designed to for parallel execution.
You cannot multitasking in a task in existing TGCS.
Yeah, but you can always separate it into two separate tasks. Then it will be like scheduled.
Yeah, separate. So this is a GPU task, pure GPU task. There must be a CPU thread, execute, offload all these tasks. How do you know as a scheduler that this GPU task is finished? You need to track. You need to track all the status, right? And they will incur some overhead. But if you can use Coroutine, you can not only express this very clear and avoid this, you can also avoid this overhead. We'll discuss it later if you are still interested in this, okay? Yeah, sure.
Yes, I'm a bit confused about how good the benchmark results are. So you showed some graphs that showed it was, what, 18 times faster? Was that accurate for some benchmarks?
Yeah, I know this is just micro benchmark.
What are the competitors doing that is so horrible that it's 18 times better? Because it seems too good.
For the test for Coro, the reason is because I use standard async. It is you create a task on the fly. So when the suspend coroutine is finished, is ready, we create an async task for this suspended coroutine. And this dynamic overhead is very large. That's why I have like 18 times speed up here.
Stood async creates a new thread every time.
Yes.
So we're just benchmarking against really bad algorithms.
Here, I want to demonstrate is that if you want to embed C++ coroutine in a existing TGPS, it is very bad. Because first, existing TGPS all assume it's not aware of coroutine. They are all aware of functions. So their scheduler are all targeting on functions, not coroutine. Second is that traditional function code is totally different from coroutines. Coroutine, you need suspend and resume. You need to schedule all this stuff. They're just not aware of that.
So we're comparing against libraries that don't themselves take coroutines into account, but you are shoving coroutines into them.
Yes. I try to demonstrate.
Don't use coroutines.
Yeah.
I feel like it would be much better than 18. Like surely it would only be twice as bad, right? Like in the worst case, if you never multitask your CPU and GPU, surely it's like twice as bad. So it feels like 18 just feels like it must be comparing against something.
So the 2 times will be like Taskflow and Taro, right? Because Taskflow doesn't support coroutine. So if you compare Taskflow, indeed, the most speed I get is 2 times. Yeah. Okay, sure.
So assume you were always having threads, 1 thread per core. You would never have multiple threads per core. You'd have a loss. So you're basically dedicating 1 thread per core.
Yeah. You mean, do I support hyper-threading like that?
I assume the performance would fall off if you had more than 1 thread per
Yeah, sure. Yeah. Because you only have the core. The core is the resource, right? Yeah. Yeah, sure.
So I had a question about the kernels. So you're compiling some CUDA kernels and you're scheduling them on individual cores on the GPU. You can probably have multiple kernels scheduled together. That's where the coroutine piece comes in because you're like waiting for data from each one of those kernels, right? So when you were doing this benchmarking, how were you doing the same thing on non-Taro implementations?
Oh, good question. I'm glad someone found that. You mean like this, right? So, no, this. Let me see. Oh, yeah, indeed this. So we have while loop. We have call wait. How do you implement in Taskflow? Simply just a linear chain of 300 nodes. It's okay because task creation is very lightweight. Yeah.
So you created those tasks linearly. How were you waiting for them? Were you waiting for them linearly after creating all the tasks? Or were you waiting and queuing the next one?
So for this while loop, here I iterate 300 times, right? I create 300 nodes, 300 linear chains together.
So let's say you did this same thing in Taskflow, right? You're queuing tasks to the GPU, and you have multiple cores on the GPU. You're queuing tasks first with the data, and then you're waiting for the results at the end, and that's when you're benchmarking the total time.
Yeah. Any questions? Yeah.
How do you compare your efforts in Taro with the STD execution P2300?
Still execution.
Yeah, the new
Scalable execution policy.
The sender receiver.
You mean like sender receiver or?
Yeah, the sender receiver.
I haven't tried that. Yeah, I'm also thinking about maybe I can support sender receiver in Taro. Not sure if I can get any interesting results. But yeah, the answer is I haven't tested it.
So you would treat those as the low-level implementation details for this framework. And the user side, they're confidently going to use your Taro API. Like sender receiver is just one thing like similar to async that you support all of the
Yeah, like like I said, I find that there are lots of things you can do in C++ coroutine, like computation patterns. How do you describe a computation pattern? How did you describe these patterns using C++ coroutine? That's actually very interesting. So that's one direction we can do. All right? Oh, yeah, sure.
Now, for example, about your data. People ask about how users supply data. All of you experiment, the code, you basically do a reference of the data in a global space. Does that mean that user define all the data outside of your framework, prepare there, and then define all the code of your task, and then in the end, like the data are totally separate from your.
Yeah, that's our decision, because we think data is so complicated. We want users to handle this, because everyone has different strategies about data. That's why. All right, so thank you again for attending this session.